Welcome to this explainer. Today, we're doing something really exciting. We are going to literally reverse engineer a factory's operations, transforming what looks like absolute manufacturing chaos into a perfectly timed assembly line. I am so thrilled to have you here for this. We aren't just skimming the surface of theoretical business concepts today, we are breaking down the microscopic, mathematical execution that keeps global supply chains running and powers the incredibly structured machine that is production and operations management. So, let's dive right into our big question. With thousands of unpredictable moving parts, how do massive companies actually prevent stockouts, idle machines, and delayed orders? Think about it for a second. When you buy a custom-built computer or a high-end car, there are literally thousands of individual, highly specific components that had to arrive at the exact right workstation, at the exact right time, without costing the parent company an absolute fortune in warehouse space. How in the world do they do it without descending into total chaos? Well, to answer that, here's our roadmap for today. We'll start with 1, the heart of operations, move to 2, feeding the MRP engine, 3, calculating perfect lot sizes, 4, planning your production strategy, 5, the rules of sequencing, and finally, 6, the critical ratio gauge.
Let's lay down our foundation with Section 1, the heart of operations.
At its core, Production and Operations Management, or POM, is the vital system that transforms raw inputs like materials, machinery, and labor into finished goods. But, and this is absolutely crucial, it operates across multiple strategic levels. POM isn't just one single thing. It ranges from high-level multi-year facility capacity planning down to tactical monthly scheduling, all the way into the super granular daily minutia of shop floor control. Whether you're making physical goods or working in the service sector, operations management is the multi-layered engine driving your productivity. And as we can see here, the main objectives are all about balance, keeping a tight leash on material and production costs while simultaneously boosting quality and ensuring timely delivery. It's a constant, multi-departmental balancing act, and honestly, it has massive inherent friction. Think of a premium auto manufacturer. You simply cannot slash production costs if it compromises the vehicle's safety features, right? And conversely, you can't build a flawless, custom-tuned engine if it takes so incredibly long that you miss your quarterly delivery windows to the dealerships. POM is the discipline of hitting every single one of these targets at the exact same time.
Now, let's look at the data driving all of this in Section 2, feeding the MRP engine.
Okay, take a close look at the flow of data here. This actually corrects a very common trap. A lot of people think the planned order report feeds the material requirements planning or MRP engine, but actually, scratch that. It's the exact opposite. The planned order report is the final output derived from your master files. To get that output, your MRP system needs 3 critical input nodes. First, the item master file. Second, the product structure file, also known as the bill of materials. And third, the master production schedule, which tells you exactly which finished products are needed and when. An effective MRP system requires an incredibly high level of data accuracy, usually around 95%, which is notoriously difficult to maintain. Why? Because you're constantly fighting real-world friction. I'm talking inventory spoilage, vendor data lags, simple human errors on the scanning floor. If those input nodes are wrong, your planned order report is going to be a complete disaster.
With that engine running, let's jump into Section 3, calculating perfect lot sizes. So, we know what we need to build, but how do we actually buy the materials efficiently? The real key here is finding your economic order quantity. This is a lot size calculation that perfectly minimizes the sum of your carrying costs and your ordering costs. It's a classic, inescapable tug-of-war. If you order too much at once, sure, your ordering costs go down, but your carrying costs, the actual money, insurance, and physical warehouse space tied up in storing that inventory, absolutely skyrocket. But if you order too little, your carrying costs are low, but you're constantly getting hit with expensive setup and ordering fees. The EOQ model finds that exact mathematical sweet spot where these two conflicting costs balance out perfectly. So how does that theoretical perfect lot size actually look on a calendar? Well, let's say your calculated EOQ is 100 units, and your average demand is 20 units. A periodic order quantity calculation dictates that you must place an order exactly every 5 weeks to meet your variable demand. You simply take that perfect lot size of 100, divided by your demand of 20, and boom, the math gives you your timeline. The periodic order quantity is incredibly useful when you're trying to sync those optimal order sizes with shifting demand cycles inside your MRP system. But, formulas assume a perfectly frictionless world, and we all know that's not reality. In the real world, an assemble-to-order manager must constantly cope with totally unrealistic demand and regularly relax those rigid MRP assumptions, simply because lead times are rarely fixed. The math assumes that when you place an order, it takes exactly the same amount of time to arrive, every single time. But what happens when a machine suddenly breaks down? What about a global raw material shortage, or a massive cargo ship getting stuck in a canal? A great operations manager understands the pure math for sure, but more importantly, they know exactly when to introduce real-world nuance and relax those assumptions so the entire factory doesn't grind to a halt over one delayed truck. Okay, let's zoom out a bit for Section 4, Planning Your Production Strategy.
We're looking at the 6 to 12-month horizon now. At this aggregate level, you've got to choose a high-level execution plan. Do you go with level production and risk losing some control over your physical output, or do you chase demand to dynamically match market fluctuations? Think back to our car factory example. With a level production strategy, you produce vehicles at a steady, constant rhythm. It is fantastic for workforce stability, but if demand for SUVs suddenly drops, you're left holding massive, expensive inventory. On the flip side, if you chase demand, you are frantically scrambling to adjust your output to match exactly what the market wants, this very second. It keeps your inventory footprint low, sure, but it creates a high-stress, overtime-heavy environment for your workers and your machinery.
Strategy is set, so now we hit the shop floor in Section 5, the rules of sequencing. We have our materials and our plan, but now the workers actually have to build the thing. This is where sequencing steps in. Think of it as the ultimate traffic cop for the factory floor. Now, it's really important to know the difference here. While scheduling tells you the time frame of when an activity needs to happen, sequencing is the strict, specific rule that dictates exactly which job goes into the machine first. When a stressed-out machine operator has 5 different jobs waiting for them at 8 a.m., sequencing completely eliminates the guesswork. Let's look at how this plays out physically. Imagine physical jobs stacked at a workstation. Using the last-come-first-serve sequencing rule, it is actually vastly more efficient to process the job that arrived last. Why? Simply because it's sitting right on top of the stack. Now, this rule, LCFS, sounds totally backwards if you're thinking about customer service at a coffee shop, where you'd always use first come, first serve. But picture a factory floor. If a heavy pallet of steel is physically dropped via forklift directly in front of a worker, asking them to manually dig to the absolute bottom of the pile to find the oldest job is a massive waste of expensive labor time. The sequencing rule has to adapt to the physical reality of the execution floor.
Finally, how do we actually know if we're winning? That brings us to Section 6, the critical ratio gauge.
We are looking for one specific number on our dashboard, 1.0. We look at the critical ratio gauge, where a score of exactly 1 means your job is perfectly on schedule. The critical ratio is quite literally one of the most powerful vital signs an operations manager can look at. Why rely on this one single number? Because plant managers simply do not have the time to read through a 50-page diagnostic report while the assembly line is moving at full speed. They need a single, instantly readable metric that distills all that complex scheduling and sequencing data down into a definitive pass or fail. Here's how you read it. If the ratio dips below 1, you are falling behind schedule, and you need to expedite that job immediately. But if it's greater than 1, no way, you are officially ahead of schedule. This perfectly enables a concept called management by exception. In a highly functional facility, managers only want to act when an alarm goes off. If they look at the dashboard and see a bunch of 1s or 1.2s, they just let the machine run. They only step in when they see a job dropping below 1.0. That is the definitive signal to intervene, locate the bottleneck, and clear that friction before the customer is ever impacted.
As we wrap up this explainer, I want you to ask yourself a question. If a perfectly balanced assembly line is the ultimate goal, how much real-world flexibility are you willing to sacrifice to achieve that kind of mathematical perfection? We've seen how tight formulas like the economic order quantity and strict sequencing rules create stunning efficiency. But we also know that the friction of the real world constantly demands relaxed assumptions and agile responses. The true art of operations management lies right there in the middle of those two extremes. Thank you so much for joining me today. I really hope you've enjoyed peeking behind the curtain of global manufacturing, and I hope you keep exploring the incredible systems that build our world.